Why quality control matters? Let's imagine two project managers. The first sees quality control as an unnecessary expense, the second sees it as an investment. Initially, the first project appears cheaper. Fewer tests, faster progress, lower immediate cost. Everyone feels they are saving money. But months later, cracks begin appearing. Concrete strength test fails, repairs become necessary, occupants lose confidence, schedules slip, costs escalate, insurance claims follow. The second project tells a different story. Every batch of concrete is tested, slump is checked, tube samples are taken, materials are verified, curing is monitored, documentation is maintained. Progress may seem slightly slower, but the building performs exactly as intended. This is the true purpose of quality control, not paperwork, not bureaucracy, risk management. Quality control protects four critical areas. First, structural integrity, ensuring the building safely carries every load it was designed for. Second, durability, helping the structure resist moisture, chemicals, corrosion, and environmental attack. Third, economic performance, preventing expensive repairs and extending the building's useful life. Finally, compliance, meeting engineering standards, contractual requirements, and regulatory expectations and the mandatory controls. One of the most valuable lessons experienced engineers learn is this: the cheapest concrete is often the most expensive concrete because every defect left inside the structure eventually demands payment either during construction or years later through repairs, rehabilitation, litigation, or lost reputation. And when quality is compromised, there are always warning signs. Some are obvious, others remain hidden until serious damage has already occurred. In the first section, we will uncover the most common defects found in poor quality concrete and why understanding them is the first step towards preventing structural failure. Teaser: a tiny crack may look harmless, but in reinforced concrete, it can become the doorway to one of the most destructive processes in structural engineering. That's where we will continue in part 2. The anatomy of failure, common concrete defects. Imagine you are inspecting a building that's only 5 years old. From a distance, everything appears normal. But as you move closer, you notice hairline cracks, small patches where the concrete has flaked away, rust colored stains beneath a balcony, a floor slab that does not look perfectly level. Many people dismiss these as cosmetic issues. Experienced engineers don't, because concrete almost always gives warning signs before serious structural problems develop. Think of these defects as symptoms, just as a doctor looks beyond a fever to find the underlying illness. Engineers look beyond visible damage to identify the real cause. Let us start with cracking. Not every crack is dangerous. Some are caused by normal shrinkage as concrete cures. Others result from temperature changes. But wide or growing cracks can indicate overloading, foundation settlement, poor reinforcement detailing, or inadequate curing. The important question is not simple: is there a crack? It's why did the crack form? Next is grazing. You have probably seen it before. a network of tiny surface cracks resembling a spider web. While it may not immediately affect structural strength, grazing tells us something important. The concrete surface was not treated properly. Rapid drying, poor finishing, or excess water on the surface often create this defect. Then there is uneven support. If the soil beneath the slab is not properly compacted or drainage is poor, parts of the slab begin settling differently. Over time, this creates differential settlement, leading to cracks, curling, and structural instability. Finally, there is spalling. This is one of the most alarming defects because it often exposes the reinforcement steel. Concrete begins breaking away, pieces fall from beams, columns, or balconies. The reinforcing steel becomes visible, and once the steel is exposed, deterioration accelerates rapidly. Here is something many site teams overlook: the visible defect is rarely the real problem. The real problem usually lies deeper inside the concrete itself. Hidden voids, poor compaction, honeycombing, segregation, improper water cement ratio. These invisible defects reduce the structure's ability to carry loads long before external damage becomes obvious. Did you know many major rehabilitation projects begin because of defects that could have been prevented during just a few hours of concreting? That's a remarkably expensive consequence for such a small window of time. Practical takeaway: never repair the symptoms before understanding the cause. A crack repaired without identifying its root cause will almost always return. Viewer engagement. Have you ever noticed cracks in a new building? Would you repair them immediately? Would you repair them immediately or investigate why they formed first? Let us know in the comments. Transition. But cracks and spalling are only the visible systems. One of the concrete's most destructive enemies works silently, hidden beneath the surface, often for years before anyone notices. Let us uncover that silent killer. Environmental threats. What are environmental threats? Corrosion, the silent killer. Imagine wrapping a steel bar completely inside concrete. It seems perfectly protected, safe from rain, safe from air, safe from corrosion. So, why do reinforced concrete structures around the world continue to fail because of rust? The answer lies in something almost invisible: moisture combined with oxygen, and in many cases chlorides from coastal environments or de-icing salts. Moisture slowly penetrates through tiny pores in concrete. If concrete is not dense enough, or if adequate cover was not provided, those contaminants eventually reach the reinforcement. That is when corrosion begins. And here is the surprising part: rust occupies 6 to 10 times more volume than the original steel. Imagine placing a balloon inside a rigid concrete block and slowly inflating it. The concrete has nowhere to go. Internal pressure builds, hairline cracks appear. Those cracks allow even more water to enter. Corrosion accelerates. Eventually, concrete begins breaking away. This process is known as spalling. By the time you see rust stains or exposed reinforcement, corrosion has been active for years. The visible damage is only the final chapter of a much longer story. This is why preventing engineering matters so much. Proper concrete cover, low permeability concrete or dense concrete, concrete, correct curing, adequate compaction. These simple decisions dramatically reduce the risk of corrosion. Many infrastructure owners assume corrosion is inevitable. It is not. With proper design, material selection, and quality control, much of it is preventable. Engineering tip is the best corrosion repair is not repairing corrosion, it's preventing corrosion from starting. That single philosophy has saved governments and infrastructure owners billions in life cycle maintenance costs. Practical takeaway: rust is never just a surface problem, it is usually evidence of deeper durability failures that require investigation. Viewer engagement. If you are inspecting a parking structure or a bridge, what would concern you most? Rust stains, cracks, or exposed reinforcement? Tell us below. Transition. Corrosion is only one mechanism that weakens concrete. In reality, structures are constantly attacked by multiple physical and chemical forces at the same time. Let us explore those hidden deterioration mechanisms. Chemical and physical deterioration. Concrete may look solid and permanent, but in reality, it's constantly interacting with its environment. Every day, every season, every year. Think of concrete as a living defensive barrier. If that barrier is well designed, it protects the structure. If it is poorly designed, nature slowly wins. One more major threat is carbonation. Carbon dioxide from the atmosphere gradually penetrates concrete, reducing its natural alkalinity. Once the protective environment surrounding reinforcement disappears, corrosion becomes much easier. Another threat is aggressive chemicals. Industrial environments, sewage systems, and marine structures often face sulfates, chlorides, and acidic conditions. Without the right concrete mix and protective measures, deterioration accelerates dramatically. Then there is freeze thaw action. In colder climates, water trapped inside concrete freezes and expands. Repeated cycles create internal pressure, leading to cracking and scaling. That's why engineers intentionally introduce microscopic air bubbles known as entrainment to provide room for expanding water. Perhaps the most misunderstood problem is permeability. Concrete does not need to be completely waterproof, but it should resist unnecessary moisture penetration. A dense, well designed mix acts like a protective shield. A porous mix behaves like a sponge. Every drop of water entering the concrete carries the potential for future deterioration. Construction myth. Many people believe thicker concrete automatically lasts longer. Not necessarily. Durability depends far more on quality, permeability, curing, and workmanship than simply increasing the thickness. That's why experienced engineers focus on quality before quantity. Practical takeaway: durability begins in the design office, but it's achieved on the construction site. Transition: knowing how concrete deteriorates is important, but preventing deterioration requires something even more systematic, a structured quality control process that begins long before the first truck arrives. The three stages of quality control. Let us visit a well-managed construction project. Before a single cubic meter of concrete is poured, engineers are already working. Materials are tested, mixed designs are verified, formwork is inspected, reinforcement spacing is checked, everything is prepared before concrete even reaches the site. This is quality control before concreting. Once pouring begins, the focus shifts. Slump test confirms workability, concrete samples are collected, proper vibration removes trapped air, placement is monitored continuously. These activities prevent defects before they become permanent. This is quality control during concreting. After placement, many people think the job is finished. In reality, one of the most critical phases has only just begun. Curing, strength testing, documentation, inspection, monitoring. These confirm whether the structure actually meets its design expectations. Finally comes continuous monitoring throughout the structure's life. Routine inspections in identity Routine inspections identify problems while they are still small. Early intervention extends service life. Delaying action increases both cost and risk. Here is the lesson every successful infrastructure owner eventually learns. Quality control is not a department, it's a mindset. It starts before construction, continues during construction, and never truly ends. Practical takeaway: every skipped inspection becomes a future uncertainty. Every completed inspection builds confidence in the structure's performance. Viewer engagement. Which stage do you think is most often neglected? Before concreting, during concreting, or after concreting? Share your experience below. Closing teaser. Repairing damaged concrete is not the hardest part. The real challenge is diagnosing why it failed in the first place. In part 3, we will explore how the world's best engineers approach rehabilitation and why the wrong repair can actually make a structure deteriorate faster.